So I'll try to spend about half my time giving a bit of an overview, and then the other half going a bit into the details of the model that I've worked on a bit more. And we'll see how we do with time. Maybe I'll even end a bit early to give other speakers some more time. And I should stress that this is work that has mostly been done with some great collaborators, all of whom are in this room. So Brian, Lorenzo, Ido, Tierney. So credit should go to them. And if I'm wrong, then blame should go to me. All right, so what is an engine? I was assigned to talk about engine models, and the natural question then is, well, what is an engine, and how does it differ from a progenitor or an emission mechanism? And so I thought about this a bit, and I think the conclusion I came to is that the engine is the sort of thing that connects everything together. It's sort of a holistic view of what the source is doing, and it connects the emission mechanism that produces the actual bursts themselves, along with what you might imagine the progenitors are doing, which ties in, of course, to stuff like localizations, and also the larger scale environment, or as Laura just put it in her talk earlier today, the system. So thinking about this not just as sources of fast rate of bursts, but thinking as the system, about these systems in a holistic view and trying to explain the myriad of different observations. So in particular, thinking about 121102, the first repeater, thinking not only about the bursts themselves, which would be related to the emission mechanism, but also about why they're occurring in this region where they're occurring in this type of galaxy, and how to explain stuff like the persistent radio emission and rotation measure. So as sort of a holistic view of the whole system, I think one of the things we can ask is, what are the models? So I tried to actually get a print screen of the whole list from this web page. This is, for those of you who aren't familiar, FRB theory catalog. So there's a great FRB catalog that Emily has curated with the actual observations of fast rate of bursts, and there's another great FRB theory catalog with all of the models that have been proposed. That's curated by Amanda and by others, Sriharsh and some others. And so I tried to actually grab a print screen of the whole thing. I just couldn't fit it. There's no way. I'm sure you can't read anything on that table, but that's fine.
I can see black hole battery.
Oh, excellent. We'll hear about that later. So perfect. There you go. That's one of the ones we'll hear about today. So the point to make about this is, of course, there are many models, right? And so how do you distinguish between these? How do you choose between these? So I think we've all in this community come to a realization that many of these models are sort of problematic, at least if you want to explain the majority of FRBs, or certainly if you want to explain particular sources that have some well-observed features. And so the first thing that is obvious is that cataclysmic scenarios, which account for a large chunk of these models that have been proposed, are quite problematic if you want to explain things like repeaters, right? That's obviously a problem. So now you can get into the whole debate of, well, okay, are there repeating and non-repeating populations? So we've heard some of that before. Just to give my own 2 cents about the way I view this. I think there are 2 ways to go about this. The first is to look at the actual observations. And from the observational point of view, it's very, very difficult to say that something is intrinsically non-repeating. So many people have gone through the exercise of either simulating these types of observations, like Manisha, and just from the observations themselves. So we heard earlier today from Vicky that 121102, from the point of view of CHIME, is a non-repeater, right? That should say everything. I think that should just, with that statement alone, I think anyone should be very, very careful about assigning something as a repeater versus non-repeater. The opposite is also true. There was an ASCAP burst that was just a vanilla non-repeating burst found by ASCAP that was recently reported to have repetitions. So you can also go the opposite way. So I think you have to be very careful. That isn't to say that there couldn't be a subpopulation of non-repeaters intrinsically, but I think there's no evidence to point that we need them. And then the second point to make, which is the point that Vikram made in a paper last year, is the rates problem. So I think from a theoretical standpoint, if you want to have truly cataclysmic one-off events, non-repeating events, you run into a crisis if you want to explain a significant chunk of the FRB population. So if you do the rates, which of course are uncertain, then you basically find that you need a significant fraction, tens of % of core collapse rate in order to produce the observed non-repeating events. So you can always get around that by introducing a model that will only explain, a very small subset, 1% or less than that of the population. That's fine. That can still be viable. But if you want to explain the bulk of the observed FRBs, I think these models are extremely problematic. So those are my 2 cents on repeating versus non-repeating. So my view is that the 0th order, they're all repeating. All right. So just to show this plot, this is a schematic cartoon I sort of drew up yesterday late at night because I was interested in this, and I think this further makes the point. So this is, we've seen this earlier actually in one of the earlier talks. This is sort of the luminosity distribution. And what I'm showing here is the luminosity distribution for 2 of the known repeaters that are localized. So I'm only showing sources that are localized so that we actually know intrinsically the fluence. There's no assumptions here about DM and redshift and how you backtrack that into distance. So this is taking basically the 2 ASCAP bursts, the DSA-10 bursts that are localized, and the 2 localized repeaters. And 2 things should be glaringly obvious. The first is that the energetics span 6 orders of magnitude. That's a huge range, right? And so we're trying to explain one phenomena, but there's actually a very deep luminosity function here. Maybe that could be telling us that there is actually more than one phenomena going on here, but I think the point to be made here is that if you sort of extrapolate these luminosity functions that are observed for the repeaters, so this is the yellow one is for 121102 and the purple one is for the chime repeater, then you'd basically expect that, if you go from 10 to the 39 or 10 to the 40 ergs to 10 to the 43 ergs, you'd expect very, very, very few bursts at these fluences. And so that again makes the point that if something like ASCAP is detecting bursts at very large distances and detecting very bright bursts intrinsically, it may just be detecting the tip of the iceberg, and it's very, very hard to follow up and see whether or not something is really intrinsically repeating there or not. The other interesting point that I want to make here is that so these power laws here are very based on different papers. So this is from Casey's paper. This is from Kelly's paper, and this is from the latest Chime paper. But there are definitely uncertainties associated with these power laws. I don't think anyone should take these at exact values. But the interesting thing, I think, is that they all range, or at least these 2 range, in the region where they're sort of flirting between deciding whether or not most of the bursts should be observed nearby. So whether or not we should intrinsically be observing most of the bursts as dim nearby bursts, or most of the bursts as far bright bursts. So this 2.5 power law is sort of what distinguishes between these 2 scenarios, and it's kind of interesting to me that we're sort of skirting the region that can be either this way or that way. All right, so back to the models. So I talked a bit about repeating versus non-repeating. What about AGN models? So another class of models that had been proposed and were talked about were scenarios where AGN, by some mechanism, produced fast greater bursts. And I would claim that these models are now somewhat disfavored given the localizations that we know not only of this dwarf galaxy where an AGN is possible but would be highly unusual, but these newer localizations where the bursts are coming from clearly non-nuclear regions, sometimes offset by many kiloparsecs from the nuclear regions of the galaxy. So I know Chris may have different thoughts about this. Hopefully he'll tell us a bit about that later, but that's at least my naive take on this. And so then what we're left with, well, there are actually many more things, but one of the big chunk of models that we're left with is neutron star models. And of course, I think everyone here in this room knows that these are widely discussed and very popular. But I'll add the caveat that maybe this is just because we have a limited imagination, or maybe I should say that about myself. Maybe me as a theorist, I have a limited imagination, and I just try to explain it in the most boring way and not think of something more exotic. So diving in a bit into neutron star models, right? We're talking about engines, and so we have to ask, what is the fuel for the neutron star, or how can you produce the bursts? What drives the emission? And so there are different options you can choose, different paths you can take. One is spin-down power. So basically, this would be something like a pulsar. We've heard about models like this. They encounter some difficulties in terms of explaining the energetics and lifetimes that we expect for these sources. Another popular model is that the energy source is basically diffusion of magnetic fields inside the core of this neutron star. So this is a magnetar, somewhat akin to magnetars known in our own galaxy. That's another class of models. A third class of models are interaction models, where basically the bursts are powered by either some kinetic flow just slamming into the magnetosphere of the neutron star, or two neutron star magnetospheres interacting with one another, or neutron star magnetosphere interacting with a black hole. And we'll hear about some of those, I hope, later. So we'll hear more about those types of models. And then the last flavor is accretion. So in some sense, you can think of these as black hole models, right? The neutron star here may not be important as in the sense that it's a neutron star. Really what you care about is just the accretion flow that drives this. And maybe you can think of something sort of anomalous to, analogous to ULXs. All right, so I'll focus a bit more on these types of models, as that's what I've worked on a bit more. And just to sort of clarify that there are still distinctions within these types of models. So we hear the word magnetar model thrown around a lot. There are actually various different versions and flavors and prescriptions for magnetar models, so there's not one unique magnetar model. So some of the different paths you can take are choosing things like where the emission actually occurs. So whether or not the emission in your model occurs in the magnetosphere of this magnetar. So this is sort of near models, where things, you have some disruption in the magnetosphere, and then you produce some radiation, say by curvature radiation or by reconnection, and hopefully we'll hear about both of those in the emission section tomorrow. So that's one option you can take, and then another option is where the emission is produced at much further distances by something like relativistic shocks. And this is, for example, the so-called synchrotron maser blast wave model. So again, just to stress, magnetar model, there is no one magnetar model. There are various different flavors and types of magnetar models, each with their own peculiarities. All right. Before I go a bit more into the synchrotron blast wave model, does anyone have comments, questions, thoughts about? Okay, the basic overview. Yep.
I just want to point out something about your dn by energy. Basically, make the statement that we have to explain over six orders of magnitude energy. Make the very quick comment that, of course, that ignores beaming. All those numbers, I think, assume isotropic beaming.
Yep.
I suspect you could shrink it by a little bit, assuming beaming, but I agree you probably can't get rid of the six-ish orders of magnitude.
Yeah, I mean, the way to get around that, beaming by itself doesn't help unless you assume that different sources have different beaming. Yeah, so you'd have to say that the brighter bursts are just more beamed for some reason. Yeah. That's possible, but yes. Yeah, good point. All right, cool. So, all right, I'll spend a bit of my time now then diving a bit more into the synchrotron maser blast wave model and some stuff that we've worked on lately. All right, so what is the basic picture? I think most of you have seen this or heard this before, but I'll go through the basics again. So the basic picture is that in this scenario, the bursts are powered by magnetized relativistic shocks. So I mentioned earlier that the engine is sort of the diffusion of core magnetic field, but really that's secondary to this model. This model doesn't actually care about the magnetar itself, per se. For the synchrotron blast wave model, what you really care about is that you have some mechanism that outputs some relativistic shocks that slam into a magnetized upstream medium. That mechanism can be a magnetar, which is sort of the favored scenario that we've thought of, but it by no means has to be a magnetar. So again, this is viewing the engine here is basically thinking a bit more about the emission mechanism and sort of forgetting a bit for a second about the large-scale environment. And I'll come back to that later. So how do you power bursts by relativistic shocks? And what even motivated us to think about that? So I should say that most of this work was driven by early work by Yuri Lubarsky and Andre, who will speak right after me. So hopefully we'll hear more on that as well. And sort of we came in a bit later, and the thing that motivated us was this observation that Jason had that many of the bursts for 121102, and now we know that not just for 121102, have this sad trombone drifting in frequency feature. And so what motivated us is that basically the shock dynamics, the fact that you have a shock plowing into an external medium and it slows down, it decelerates, that can explain possibly the frequency drift in this sad trombone feature. And so how do you do that? So this is a schematic. The schematic is that you have here the engine, whatever it may be, and that engine emits some relativistic flare, and that's that orange region. And the relativistic flare will then slam into some upstream medium, which in our sort of fiducial model is some sort of baryonic shell previously ejected by the engine. And we'll get into some distinctions about that later on. So when this flare slams into the upstream medium, into this green region, of course you produce a forward and reverse shock. Okay? But the interesting point is that if this upstream is magnetized, it has a strong magnetic field, or more importantly, the magnetization, so the ratio of magnetic to kinetic energy is of order unity, then what happens is actually, instead of these shocks being like regular GRB shocks, where you have diffusive shock acceleration of electrons and amplification of magnetic fields, what happens is you actually get coherent radiation, coherent Larmor gyration of particles around this magnetic field, and that produces coherent radio emission. And so this forward shock is now propagating with some Lorentz factor into the upstream medium. You produce the FRB via the so-called synchrotron-maser mechanism, which we'll hear more about from Lorenzo. And then the idea is that as this shock plows the upstream medium, it slows down. So the Lorentz factor decreases, and that causes basically the photons, you can think of them as being redshifted, right? You basically slow down the shock, and you move your emission from peak emission from bluer bands, so from higher frequencies, to redder bands, to lower frequencies. Okay? And that's sort of the picture that is we have in this scenario. Now, another interesting thing is that you have some well-defined polarization angle and high polarization fraction. And again, we'll hear more about that from Lorenzo. So the basics is that the shock then determines all of the observables. So if you know, if you want to know what the observed luminosity is, all you need to know is what is the Lorentz factor of this relativistic flare, and what are the properties of the upstream medium that it runs into. So what's the density of this upstream medium, and where is this shock occurring, at what radius? But of course, you can also relate the duration of the burst to these same quantities. This is just the standard expression familiar to people from the GRB literature. So the duration is just proportional to the radius at which the shocks are happening divided by gamma squared. And then the frequency is related to the intrinsic emission mechanism, the synchrotron-maser emission, but it's basically, it turns out to be something like the Lorentz factor times the plasma frequency. So again, it's related to the Lorentz factor of this relativistic material and the external density that it runs into. And so if you take all of these observables, you can actually try to reverse engineer and take the actual observations and find what do we infer for the local source properties. What kind of Lorentz factors, densities do we infer if we imply this, apply this to actual observations. And so that's what we did, and I'll show you some of the results that we found. And so this is sort of one plot showing the derived properties. So it's a messy plot, but what it shows is as a function of burst energy. Again, this is isotropic equivalent, okay? And this is not the observed energy in radio, not the observed fluence. This is the energy of the flare itself. This basically accounts for this inefficiency that was talked about earlier that Ellie mentioned, this 10 to the minus 5 or 10 to the minus 6 efficiency that we have within our model between the radio and the actual flare energy. And then you can also see where what are the properties of the upstream medium. So we infer densities of order hundreds or so, or thousands, where these shocks are occurring. So radii of 10 to the 12 or 10 to the 13 centimeters, and Lorentz factors, order of several hundred or so. And this is for different samples of different bursts. There's 121102 here. That's the yellow. The purple is the newly localized chime repeater. The green ones are the localized ASCAP and DSA bursts. So you see that they fall way high up in energy for the same reasons that I showed earlier. And then there's some other chime repeaters and non-repeaters there too. All right. So that's sort of just a barrage of properties, but that doesn't tell us much. So what else can we learn? So one interesting thing that we can learn is we can look at the drift rate. And remember, that was one of the motivations for this work. It was thinking about how to explain the sad trombone feature. And so if you basically look at the drift rate, basically how fast is the frequency declining as a function of time, you can sort of backtrack that it is related to the power law, well, in this parameterization, a power law density profile. And so basically you imagine that the external density is just some density with r to the minus k, and then you have some free parameter k. Now, of course, this power law doesn't have to persist for decades in radius. It can be a very local quantity. So really, you should think of this as sort of the logarithmic derivative of the density at the location where the shocks are happening. And the point is that you find a diversity in these numbers. So they all sort of hover around the value of 0, which is sort of constant density-ish, but not precisely. 2 is what you'd expect for a wind environment. And if you have negative values, that actually tells you that you're running into a density that is actually increasing and as a function of radius. So basically, as the shock moves outwards, it sweeps more and more mass at a higher rate. And so this to us signaled that maybe this is consistent with a model where what this thing is running into, what the external medium actually is this baryon-loaded shell, so this ion shell that was ejected previously. And this is sort of a schematic, a cartoon showing this. So this is maybe one way that the density could look. You have some inner bubble that's inflated by the actual rotational pulsar wind nebula, and that would have a power law slope of 2. But that's not consistent with the observations. And then you have some outer region, which is much denser, which is this baryon-loaded shell. And that's, for some region in radius, sort of constant-ish, and would give you some values that are close to, but maybe possibly a bit below 0. So that was one thing that we thought was interesting. What else did we think was interesting? So in terms of energetics, what did we find? So I showed you the energies per burst. You can also use then the implied rates for the chime repeaters and say what are the average E dots. And so this is a plot showing that. The purple, again, is the newly localized chime repeater, and the yellow is the original 121102 repeater. Okay. All of the other sources on here, we don't actually know the distance, and so things scale with distance a bit differently. These arrows show how things scale with distance. And so if you put this source in a bit closer, then these markers would shift. But for the purple and the yellow ones, we know the distances, and so that's pretty secure. And the interesting thing that we find is that within this model, the on average E dot, of course, we know that the emission is actually highly clustered and non-Poissonian and not continuous. But if you average, is of order 10 to the 39, 10 to 10 to the 40, or even a bit higher. Ergs per second, which is quite interesting. So then you can also ask, well, for an implied or inferred source age of 10 years, what does that tell you about the total energy that needs to be emitted and the total energy reservoir? And you get these types of numbers. And the question you can intuitively ask is, well, what kind of engine, right, can produce these types of E dots on average? So one answer, it won't surprise you that I'm standing here and saying this, but one answer is that it's possibly a magnetar. And so if you run in through the numbers of what you might expect for magnetar activity, then you get these types of numbers, and this is largely based on work by Andre and others. Okay, so the E dots are quite large and point possibly towards a magnetar. The other interesting thing is that this is quite remarkable, I think, is that the E dots that we find are actually consistent and in line with the E dot implied by observations of the persistent source for 121102. And so that's completely, nothing necessitated that this would be the answer, right? I'm looking at the bursts themselves, at the FRBs themselves, inferring properties about the average E dot from the bursts, and then I find some number. And sort of by surprise, it happens to be that this number coincides and works well, aligns well with the E dot that is inferred by completely separate arguments, just looking at the persistent radio emission from 121102. And to me, that's at least a strong hint that maybe abandoning these type of unification models where you can explain everything within one model is maybe premature. That isn't to say that there isn't another answer out there, but I think this is still quite striking.
And it's also consistent with the lack of such a persistent source.
Yeah, so I can mention that a bit in more detail, but so you see that the implied E dot for this new repeater is about an order of magnitude below the implied E dot for 121102. Now that doesn't seem like a lot, 1 order of magnitude, but 1 order of magnitude in E dot within our Magnetar model is about a decade in age. And a decade in age is a significant reduction in the persistent source luminosity. And I'll show that a bit later in the slide. And so it is in line with that. And actually, this is the next slide. So this is showing that. This is actually, I forgot that I had made this plot more than a year ago, maybe 2 years ago, and I hadn't really put it in anywhere. I don't remember if I showed this at any meeting. So this a bit of a messy plot is showing the interesting thing that you would expect within the model of our Magnetar model for the whole environment, explaining the rotation measure and the persistent source, that there would be a correlation between the rotation measure and the persistent source luminosity. And so that's what I'm showing here. So on the x-axis, you see the rotation measure that you might expect to observe for different sources. This is 121102. On the y-axis, you see, well, you should really look at this, which is the distance. You can also, with some model, invert this to write the dm of the IGM that you observe an event at. And the thing to note is these contours. And these contours show the 10 gigahertz radio luminosity. Within our fiducial model, again, this is taking some set of parameters that happen to fit 121102, not doing a systematic study and saying, well, what if I take this model and say all FRBs are produced with this model? If I measure a rotation measure, what do I expect the persistent luminosity to be? And so the answer is quite clear. If you measure very low rotation measures, you expect the persistent source luminosity to be very, very low. And so I think this is the Masui burst, and I plotted on here yesterday night the new chime localized repeater 180916. And you see that the limits are, again, this is just one set of parameters for a fiducial model, but you see that basically you get a, 3 order of magnitude reduction in the persistent source luminosity if you take a rotation measure of 10 instead of 10 to the 5. Or sorry, 100 instead of 10 to the 5. And so I think that's the point to be made here. And again, this is just for one fiducial model, and this plot was made about 2 years ago. So I haven't, tweaked anything here to try to fit anything. All right. So I think the point to be made then, also going back to unification models, is that, yeah.
Sorry, if I can just ask a quick question. So in this model, the sources evolve along these contours?
Yeah, so sorry, yeah, I should have mentioned this. So the source evolves basically from right to left. So you imagine that the source is at a fixed distance. So on the y-axis, it's at a fixed location, right? It always has the same intergalactic dm, or the same luminosity distance, but it evolves from right to left.
Okay.
So as age progresses, you basically move, you can see an age axis here, you move from right to left, you move from high rotation measure to low rotation measure, but at the same time, right, if you're here, then this contour tells you that you have, persistent source of 100 microjanskis, whereas if you move to here, it would be 10 to the minus 1 microjanskis.
So this argues that the RM should be declining and the persistent source should be getting fainter.
Exactly. And so there's a correlation between the two, yep. And so maybe it is unusual that we have only seen this sort of bimodality of low RM, no persistent source, high RM, high persistent source, and nothing in between. I would agree that that might be somewhat unusual, but the fact that you have these two extremes align is very natural within this model. And then the other point about persistent sources and not immediately, I think, abandoning these types of unification models had to do with the environment. And so in recent work with Ido and Brian, following the reported localizations to massive galaxies that are non-storm forming, we sort of scratched our heads at what might be able to produce magnetars or neutron stars in regions that have old stellar environments. And the answer that came to us immediately was, well, maybe in a subset of binary neutron star mergers, you can leave a stable magnetar remnant behind, and that can be active as a fast radial burst source. Or alternatively, maybe you can form these types of systems through accretion-induced collapse, and that would also be expected to happen in older stellar environments. And the interesting thing about those types of models, so you see sort of regions in parameter space where these models fall, and the parameter space here is what you might expect for the magnetar engine activity. And this sort of weird combination of parameters, which is basically the density of the ejecta surrounding the young magnetar. And so when this magnetar is born, it has some basically ejective material around it that's surrounding it. So in the case of a regular magnetar or neutron star, you might imagine that this is just the ejecta of a supernova. But in the case of a binary neutron star merger, that might be the kilonova ejecta that was ejected during merger, or the ejecta from an accretion-induced collapse. And so the point is that if you have lower densities surrounding this magnetar, then the whole system evolves on much faster timescales. And so again, you get a reduction in the rotation measured in the persistent source radioluminosity on much, much faster timescales. And again, it's very easy to explain within these types of models the lack of persistent emission. So I think the point to make is it might be a bit premature to completely abandon these types of models, even though we haven't detected any additional persistent sources yet, and the rotation measures that people have been measuring so far seem to be much lower than 121102. So I think I'm out of time. I'll leave this laundry list of open questions because I think we might discuss some of these later on in the panel session. So there are some various different open issues and caveats within that are sort of theoretical nitty-gritty details that have to do with the model. And hopefully, I'm sure we'll discuss many of these later on. And then more broadly, I think these are sort of the bigger questions that I have had recently, certainly the periodicity and many of the other things on this list. And I'll stop here. Thanks.